Hello and welcome to this last lecture on finite field for error control coding. My name is Sumit Kumar Chaube and today we are going to discuss some of the properties of extension field that we have learned in the last lecture. So in the very last lecture we learned about the Galois field GF2 to the power m, and we discussed some of its properties but not all of them. So in this particular session we are going to discuss some more properties of Galois field GF2 to the power m. Okay, so as we have seen in the GF2 that there are going to be certain polynomials which is going to be irreducible. It means they cannot be factorized any further. So those polynomials which are basically irreducible in GF2 can be actually factorized in some GF2 to the power m. For example, here x to the power 4 x cube plus 1 is irreducible in GF2, but however it is going to be reducible. It can be factorized in GF2 to the power 4, and one of the possible factorization is this, that x4 plus x cube plus 1 is actually equal to x plus alpha to the power 7 into x plus alpha to the power 11 into x plus alpha to the power 13 and x plus alpha to the power 14. So you can see this 4-degree polynomial has 4 roots, and these roots are alpha 7, alpha 11, alpha 13 and alpha 14. Okay, and this is actually very easy to show. If you multiply, let me multiply alpha 7 and alpha 13 together. Let me multiply this one together and these two together, then I will get basically here, let me write it here only, that I will be getting x6 square plus alpha 7 plus alpha 13 times x plus this is going to be our alpha 20, and the second one, when we are going to multiply alpha to the power 11 and alpha to the power 14, I will be having x square plus alpha 11 plus alpha 14 x plus alpha 25. And as we already know that alpha to the power 15 is going to be 1, and we can utilize this actually table here to reduce it. So this 25 will be equal to actually alpha to the power 10, and this 20 will be actually equal to alpha to the power 5. Similarly, alpha to the power 7 plus alpha to the power 13, you see alpha 7 is alpha cube plus alpha plus 1, and alpha 13 is alpha cube plus alpha square plus 1. So we will have alpha square plus alpha, and you see that actually alpha square plus alpha is actually equal to alpha to the power 5. So this will become alpha to the power 5, and alpha 11 and alpha 14, if you add them together, alpha 11 and alpha 14 here, you will again have alpha square plus alpha plus 1, which is alpha to the power 10. So this will be equal to alpha to the power 10. So if I will do all those things, then this multiplication will be simply equal to x square plus alpha 5x plus alpha 5 times x square plus alpha 10x plus alpha 10, right? And we can multiply them further. So this will be equal to x to the power 4 plus alpha 10 x cube plus alpha 10 x square. And in the second line, when I will multiply alpha to the power 5x with the second polynomial here, I will get alpha to the power 5 x cube plus alpha to the power 15 x square plus alpha to the power 15 x, right? And in the third column, when I will do this, it will result in alpha to the power 5 alpha 5 x square plus This is again going to be alpha 15, right? Then you will have alpha to the power 15. So if you reduce this, the result is going to be x to the power 4 here, and alpha 10 and alpha 5 is going to actually give you alpha 10 and alpha 5. If you see this here, alpha 5 and alpha 10 is hidden here, this will be actually equal to 1. So this is going to be x cubed. You can verify that there. And these three, when you add it together, is going to be equal to 0. These two XOR going to be 0, and then you have alpha 15, which is equal to 1. So this is the result, right? So let's move on to some of the properties of Galois field. And the very first property or theorem is that let fx be a polynomial with coefficient from GF2. So we have a polynomial in which the coefficient of the polynomial are from GF2, and let beta be an element in extensor field GF2 to the power m. So beta is basically a element in GF2 to the power m. So if beta is the root of this polynomial fx, then for any L greater than equal to 0, greater than equal to 0, beta 2 to the power L is also going to be root of fx. And this is very easy to prove actually, that if that f of beta is equal to 0, this is what it means, then it automatically applies that f of beta to the power 2 to the power L is also going to be root of this polynomial, right? So it's very easy to prove it. We have already seen one of the theorems, that if you have f of x, then f of x to the power 2 to the power L is actually equal to f of x 2 to the power L, right? And if you put simply beta in place of this, then you will have f of beta 2 to the power L is equal to f of beta 2 to the power L, right? So this is clearly equal to 0. We have already assumed it. Then f of 2 beta 2 to the power L is also going to be 0, right? So if f of beta is root of any polynomial f of x, then beta 2 to the power L is also going to be root of that polynomial. In fact, beta and beta 2 to the power L for L greater than equal to 0 are called conjugate. So this is a term which is already familiar with you. We have already seen complex conjugate in ordinary algebra or in complex algebra, and here we have again conjugate, that if beta is a root of a polynomial, then beta 2 to the power L is also going to be the root of that polynomial, and beta 2 to the power L for L greater than equal to 0 are called conjugate. So they are conjugate, okay. The next theorem is that the 2 to the power m minus 1 non-zero element of GF2 to the power m forms all the root of x2 to the power m minus 1 plus 1, and it is actually very easy to prove. We already know that if beta is a element of GF2 to the power m, then beta 2 to the power m minus 1 will be equal to 1, right? This is always going to be equal to 1, isn't it? So from here you can say that beta 2 to the power m minus 1 plus 1 is also equal to 0, isn't it? So you can say that beta is actually a root of x to the power 2 to the power m minus 1, isn't it? So beta is a root of 2 to the power m plus 1. So this the degree of this polynomial is 2 to the power m minus 1. So all the roots of this Galois field GF2 to the power, all the element of this Galois field GF2 to the power m will be the roots of this polynomial. In other word, all the elements, I mean, we have considered only non-zero element here, but another corollary here is that x to the power 2 to the power m plus x, the roots of this polynomial actually gives us all So roots of this polynomial gives us all elements of GF2 to the power m. So this is another property that we have to know. Now there is a definition, and this is the definition of a minimal polynomial. We have already seen some of the definition, but this is the definition of minimum polynomial. So minimum polynomial is the smallest degree polynomial over GF2 such that beta is root of that polynomial. Okay, so phi x is called a minimum polynomial of this element beta if it is the lowest degree polynomial for which beta is a root. Is that clear? And the theorem here is that minimum polynomial phi x of a field element beta is irreducible, and it's also very easy to prove. One can simply, let's say that phi x is actually irreducible, then phi of x can be written as phi 1 of x times phi 2 of x, right? And if we put beta here, then we will have phi of beta equal to phi 1 of beta times phi 2 of beta, but phi of beta is equal to 0. So it means that this is equal to 0. What does that implies? That either this one is equal to 0 or this one is equal to 0. Either phi 1 beta is 0 and or phi 2 beta is 0. Then phi beta cannot be the minimal polynomial, because the minimal polynomial has to be the smallest degree polynomial over GF2, right? So that is going to be that's going to be a contradiction here. So if it means that our assumption here that phi x is reducible is wrong. It means phi x is not reducible or phi x is irreducible. So minimal polynomial of a field element beta is going to be irreducible. Okay. Now there are certain other properties here, that let fx be a polynomial of GF2, let phi x be a minimum polynomial of a field element beta. If beta is a root of fx, then fx is divisible by phi x. Since phi x is the lowest degree polynomial for which beta is the root, then if beta is root of this, then this must be divisible by phi x as well. And it's actually very easy to prove. The minimum polynomial phi x of an element beta in GF2 to the power m divides x2 to the power m plus x, and this is also very easy to prove. This is another property that we have to consider. Now how to determine this polynomial, minimum polynomial, and this is something that we are actually going to discuss. Okay, so let's say e is the smallest integer such that beta to the power 2 to the power e is equal to beta. Means after e, it's going to repeat itself, isn't it? This is going to repeat itself in the circle. Then phi of x is basically multiplication from I equal to 1 to e to minus 1 x minus beta I. Okay, or x plus beta I. I mean, it's okay, x minus beta I. There is no problem there. You can do that. Okay, is it clear? So this is how you can actually calculate this polynomial. Okay, let phi x be the minimum polynomial of an element beta in GF2 to the power m. Let e be the degree of phi x, then e is the smallest integer such that beta 2 to the power e is equal to beta, and that's actually follows this theorem only. So these theorems are important. They are going to be used in actually BCH code. So for BCH code we have to determine minimum polynomial, and there we have to know how to determine this minimum polynomial. Okay, and the degree of minimal polynomial of any element GF2m divides m. It's also very easy to show, and one can do that. So these are some of the properties that one has to know in order to understand error control coding. Okay, so I hope that you revise them, you try to find proof of them, or you can easily prove all these properties. So do that and revise that. In the next session we will discuss BCH code. Thank you.